Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 7th, 2025, about 7 days ago. It introduces an open-weight 12.7 billion parameter model that uses grouped differential attention to rival much larger systems, posting about 95% on GSM 8K, 74% on math, 66% on human eval, and 82% on MBPP, while training on 5.5 trillion tokens. The paper is titled Motif-2 12.7B Technical Report, and as we'll see later, the implications for model training are quite significant. Alright, Table 1 lists the core hyperparameters for the 12.7 billion parameter model. The upper block details dimensions and head counts. Hidden size 4096, 40 layers. Feed forward 16,384, 40 heads, with 16 key value heads and 8 noise heads that regulate distracting signals. The lower block captures mechanisms and limits, grouped differential attention, PolyNorm activation, rotary positional embeddings with theta about 1 million, a 32,000 token context, and a vocabulary near 219,000. Well, Table 2 compares benchmark results across model families and highlights leaders in bold with runners up underlined. The 12.7 billion model posts strong math and reasoning scores, with about 95% on GSM, 8K, and 74% on math, and it delivers competitive coding results at 66 on human eval and 82 on MBPP. General knowledge metrics sit in the upper 70s, which keeps the overall average near 72. These results show parity with larger open weights and clear gains over similarly sized peers. So, while Table 2 emphasized accuracy, Table 3 reports system gains from fused kernels. Table 3 shows large speedups on an H200 GPU. PolyNorm reached about 30 times faster forward and 44 times faster backward than the naive baseline, and the fused PolyNorm plus element-wise multiplication still delivered roughly 23 times forward and 28 times backward. The fused approach also beat torch compile, especially in the backward pass, which matters because training spends heavy time there. So while Table 3 highlighted kernel speedups, Figure 1 shows how parallel Muon moves data using all-to-all communication. All-to-all means every device exchanges shards with every other, so each rank gathers the full gradients it is responsible for. The left panels depict sharded gradients per rank, and the right panels show the regrouped full matrices ready for local Newton-Schultz updates. This redistribution removes redundant work and sets up concurrent computation across ranks. So, while Figure 1 showed the data reshuffle, Figure 2 illustrates a pipeline schedule that overlaps gather, compute, and scatter. The top timeline separates these phases, which leaves long, idle gaps. The lower timeline pipelines chunked work, so scatter for the previous chunk, gather for the next, and compute for the current run concurrently. This overlap cuts wall time and also lowers peak memory, because completed full matrices can be released sooner. Optimal chunk size balances find overlap with efficient bandwidth. Alright, while Figure 2 outlined the pipeline, Table 4 reports measured performance on 8 H200 GPUs. The non-pipeline parallel Muon reaches about 571 tera floating operations per second per GPU, roughly 7 times the distributed Muon at 80. Pipelining alone drops throughput to about 481 because chunked all-to-all creates imbalance, but flop-sorted scheduling lifts it to about 583. Crucially, pipeline variants cut peak memory from about 12 gigabytes to roughly 3 to 4 gigabytes, and step time falls from about 1.6 seconds to around 0.22 seconds. Okay, while Table 4 quantified system throughput, Table 5 compares performance across Motif-2 and Qwen families. The 12.7 billion instruct model hits about 90 on MMLU Redux and 97 on Math 500, which places it near larger Qwen 3Think variants. Scores on AIME24 and AIME25 reach about 72 and 64, trailing the biggest models by several points. The average lands near 67, showing strong efficiency given the smaller scale and data. Alright, 2 takeaways stand out. Grouped differential attention plus a smart depth scale delivers big capability at 12.7 billion parameters, and the system's stack, fused kernels with parallel Muon, turns that design into practical speed and memory wins. The broader implication is clear. Mid-sized open weights can rival larger models efficiently. That is it for the AI Research Roundup. I am Alex. Thanks for listening.